Thank you very much, and welcome to this talk on the energy interface challenge. I think basically we are living in a world of climate change and have the challenge to reduce transport emissions. So a good question is, what can we as automotive interface researchers do for sustainable mobility? And I think we can do a lot. So we can guide users towards energy efficient driving. We can increase awareness and understanding of energy efficiency, and we can support energy-related decision-making. And this is important because energy efficiency is always the product of technical potential and user behavior. So for any technology to realize its energy efficiency potential, may it be automation or electric vehicles, we need user acceptance and we need optimal user behavior. So the question is thus, how can we design effective energy interfaces that make eco-driving as easy as possible? And for this to happen, we have to integrate knowledge from engineering and psychology to answer two questions, which are, what is actually energy efficient, and how should we best condense and represent the energy flow data into meaningful information interfaces to align with human information processing? So what we need are user-centered efficiency metrics and indicators to design effective energy interfaces. And here it's interesting to note that energy interface design is about two things: data aggregation and data representation. And while there's generally surprisingly little research on the topic, there's particularly little research on the user-centered design of data aggregation. So in this talk, I want to focus on this topic, focusing on battery electric vehicles as a prototypic vehicle and on manual driving scenarios, because they will still constitute a large share of driving contexts with higher energy management demands. Okay, so what is actually energy efficient? This is the answer we present in the paper, but for now I want to break this down a bit and focus on one specific scenario. Let's say I want to go to my favorite beach at the Baltic Sea, so near Lübeck. So what is the most efficient way to drive the 40 kilometers to the beach? The most efficient way is, of course, to use the bicycle. Okay, let's say I have to take the car, then the most efficient way is to take the 30 kilometers route to the beach. Here it's interesting to see that our most common energy efficiency metric, which is energy per distance, so for example kilowatt hours per 100 kilometer, has a blind spot because it gives us no incentive for taking a shorter route. So what we need are user-centered metrics and indicators that correct this bias and make users aware of this blind spot. Okay, let's say I took the shortest route, then what is the most efficient way to drive the 30 kilometers to the beach? If you drive with constant speed on a flat road, like in northern Germany, then you basically have two resistant forces. First, rolling resistance, which is constant based on the road surface, and second, aerodynamic resistance, which increases quadratically with speed. So the cost of driving 10 kilometers per hour faster increases with speed, while at the same time, the time savings decrease. So this is also something that we should help users trade this energy consumption against travel time. Yet there's one important further factor, which is electric motors are most efficient at moderate speeds, so for a typical battery electric vehicle. So that's what this efficiency map here shows. So for example, a speed of 60 kilometers in a pedal position of 40% is in this green efficient area, so it has a high conversion efficiency. Okay. Unfortunately, as we all know, life is more complex than just choosing the correct speed, right? So it's about a lot of deceleration, acceleration maneuvers, and this here is just a 5-kilometer driving segment. So how do humans actually control their behavior in such a dynamic and complex environment? I would say basically in every drivers typically balance different driving goals, right? So we want to get there alive, in time, stress-free, with reasonable energy costs maybe, and without disturbing other traffic or passengers. And drivers continuously adapt their behavior to balance these goals. Such dynamic aspects of behavior have been and can be particularly well be modeled with control theoretic frameworks. Yet most of these frameworks so far rather focus on explaining safety-related aspects of driving behavior, and only recently we have proposed a very preliminary working model for structuring the control of energy-related behavior. Now, I don't want to go into this now. I rather want to point out one interesting fact, which is, what do safety, time, energy, and pleasure have in common? They are all resources, and all resources are subject to the same psychological principle, which is we strive to achieve gains and avoid losses. However, as we all know, we are not completely rational. We are driven by bounded rationality, so we fall for heuristics and biases also in the driving domain. Thus, basically, the control of energy flows in vehicles is the economic transaction of an input resource, like electrical energy, for an output resource, so distance-driven, for example. And the key mechanism of behavioral economics is that resource transactions can be framed differently. So the same resource states or energy flows can be represented as either gains or losses. And any energy interface design, in the end, constitutes such a framing. For example, an acceleration. Nowadays, drivers typically have one salient information source to perceive the efficiency of their current acceleration, which is the instantaneous consumption indicator, which is based on this energy per distance metric. However, first research shows that there's a risk that drivers have difficulties deriving the actual efficiency from these acceleration indicator or consumption indicator, because they tend to concentrate on the peak height and rather neglect the peak duration. So the question is thus, how can we accurately represent energy consumption for accelerations? From the problem sketch above, an easy and maybe promising solution to debias perception is to represent an instantaneous consumption trace. This also has the advantage that drivers are less distracted by such transient information states as in the instantaneous consumption indicator as it's commonly implemented. Yet still, as you can see here in the interface concept that we propose, information density is high, so we have to reduce perceptual workload, for example, using gestalt doors or emergent feature effects, for example, by using metaphors like energy terrain. However, this energy per distance metric is not the most accurate framing of what happens in accelerations, so the resource transactions that take place in accelerations. Indeed, an acceleration is investing electric energy to build up established kinetic energy. So accelerations should take place at the highest possible conversion efficiency of these two resources. Thus, the metric is gained velocity per invested unit of energy. And interestingly, we can derive this from the data of this efficiency map that I showed before. So a possible indicator based on this data would be the instantaneous conversion efficiency based on drive pedal position and speed. So if you imagine this efficiency map would be a cake viewed from above, and then we cut the cake in two at a certain vehicle speed, and then we look at the piece of cake from the side, then we have this terrain profile of possible conversion efficiencies given this speed and the current conversion efficiency given the pedal position. So how does this look in the real world? For this, we have set up an interactive energy interface test environment in our BeamNG Research driving simulator and in our Renault Zoe, where we implemented plug-and-play data interface and a progressive web app. And this is how it looks. So that's from our test drive last week. So of course it becomes clear that's quite distracting still, right? So in its current form. So this interface has to and it can be optimized for example, peripheral perception. And we could also add vibro-tactile or auditory, so sonification information. So the visual information could just be learned, used to learn the mapping. Okay, so conversion efficiency is a possible step forward. With regard to accurately framing energy efficiency, there's just one problem, which is this indicator only incentivizes efficiency of accelerations without penalizing unnecessarily acceleration. So from a behavioral economics perspective, you could say there's a too narrow framing. So what we need is an additional metric that shows when too much kinetic energy has been built up compared to what can efficiently be utilized. And this can be at least partly be solved by accurate deceleration matrix that, for example, show how far kinetic energy would last given different driving modes. Yet here, a lot of things have to be taken into consideration, so designing something like this is not that easy. Okay, what do we take from this talk? I think we must reconsider how we represent energy efficiency in vehicles and how to better align this with human information processing, behavioral economics, and the actual energy efficiency. So the key challenge is, from our point of view, to find the optimal aggregation of energy flow time series data. And of course, many open questions remain, like the integration with automated driving functions. So how do we optimize automated driving functions for energy efficiency and keep the traceability of why is this actually energy efficient, and adapt to the dynamic changes in driver preferences? And how do we make the abstract concept of electric energy more tangible and reduce psychological distance? And how do we address the important topic of user diversity, like motivation for eco-driving or the affinity for technology interaction? If you want to read more, then check out the paper and the references, or get in contact. Thank you.